In this video, we will introduce concepts related to normalizing relations in a database, normalization, is part of the concept of the relational database, accredited to Dr. Edgar Frank Codd, who at the time was an employee at IBM. We study his work to this day because he invented something that we use to manage transactions and transactional information in a database, which is very important to computer science, database managers, database analysts, database programmers, and database developers. After you finish this sequence of presentations, this is what you will learn to do. You will take a relation, or if you will, a table, that is not in a reasonable normal form, and you will convert it to one or more new relations that are normalized to what we call BCNF, or Boyce-Codd normal form. Notice right away there is no data. We're doing this in a formal manner, not in an intuitive manner. We don't normalize by looking at data. I'll talk more about that later. For our purposes, we can think of a relation as a table. We will look at something called a logical design, which is a pre-table, something that is created before the actual table in the database is created. We can also look at a relational database as a way of storing information in relations or in tables. The word relational in a relational database means that we are storing in tables. It does not mean that the tables are necessarily somehow related, although they usually are. We can also store relations or tables in a database that are not at all normalized. It's not a rule that a relational database has to be normalized to any level. So when we say we have a relational database, that does not mean we have any kind of normalization specifically. We usually do, and we prefer that we do, but one does not necessarily require the other. Make sure that you are comfortable with these definitions. If you need to stop and do some research, refresh your memory as to what all of these terms mean. We will be using some of these throughout our presentations, and you'll have a much easier time understanding what we're up to if you know what these terms mean. New terms we are introducing: a prime attribute is an attribute or a column that appears in one or more candidate keys. A non-prime or non-key attribute does not appear in any candidate keys. Most tables will have attributes that are prime and attributes that are non-prime. Both of these are common. For our purposes, as database developers existing in the real world, we will assume every table has a natural key. Without a natural key, it's impossible to differentiate one record from another in the real world. We could, of course, add a surrogate key, but that does us no good as far as presenting data to the customer, because as far as the customer is concerned, we could have some duplicate rows, which are at the least confusing and at the worst detrimental to the operation of the database. Therefore, every table must have a natural key. That natural key must come from the customer domain, from an expert in the way that the data is organized in the real world. That might be you, that might be a systems analyst with whom you work, that might be the customer for whom you are developing the database. We normalize to eliminate data that's repeated in a table, not all repeated data, but some of it, to eliminate data that's not related, that might exist in a table that has no reason to be there, and to eliminate some of the possibilities of making mistakes when we're updating the table or deleting rows from a table. When we talk about optimal performance, there are two types at work. One is when we want to insert a row, delete a row, or modify an existing row in a table. Those we refer to as updates. A properly normalized database is optimized for those type of changes to the database: inserts, deletes, modifications. A properly normalized database is not, however, optimized for pulling rows out of the database for reporting. So in this case of an exceptionally large database, where joining tables together through foreign keys could take a long time, we may give up some normalization to get optimal performance for retrieval. That's a different kind of database. Some may refer to it as a data warehouse, wherein we are not as normalized as we might be because we understand the risks. We don't plan to insert, delete, or modify, but we do plan to retrieve like crazy. And in that data warehouse, since we want to retrieve and retrieve and retrieve, we need to optimize for retrieval, and that requires giving up a little bit of normalization. In our world, however, we are still transactional. We are still interested in normalizing to BCNF. And be sure you understand, very important, that we normalize the schema. We do not normalize the data. In some cases, I will be showing you data just to illustrate a point, but we do not need data to normalize to BCNF. You may read websites, you may read books that use intuition to achieve some level of normalization based on the column headings in the table, even based on the data in the table. Not a good idea. We are normalizing in a more formal manner using functional dependencies and determinants, which we will arrive at shortly. Do not study the data. Do not study the column names. Study the functional dependencies and the determinants and how to normalize using those facts. Now, to get the functional dependencies and the determinants, we must have domain knowledge. We must understand how this data works in the real world and how it maps into our relations. If we don't have domain knowledge and we can't define dependencies and we can't define determinants, then we can't normalize. I don't like to say this table is normalized because it doesn't specifically tell me to what level the table is normalized. You will run into some situations where people will say it's normalized and they are inferring or implying from that it is 1NF or that it is 3NF. But I would prefer you to be more specific. I would prefer you to say, when this table is normalized to 3NF, to 2NF, to BCNF, or to 4NF, rather than just saying this table is normalized. This is just a better way to think about the problem and a better way to be more specific when you describe the tables that you're working with. This is also a raging debate on nerd websites like Stack Overflow, where you can get both opinions about how detailed you have to be when you say something is normalized. I'm not interested in a debate. I just want to be sure that we are all using the same terminology for the purpose of this presentation. Here we introduce the concept of a functional dependency, sometimes just called a dependency. and the concept of a determinant. We have a column A in our table, and if we know the value in column A in a particular row, then we can tell, we can determine, we can decide, we can calculate what the value is in column B of that same row. A particular cell in the table then, called column A, can determine a particular cell in the same row called column B. In this case, A would be called a determinant, and A determining B would be called a functional dependency. B is functionally dependent on A. So this is the basis for normalization. This concept is what we use to create normalized relations and to decide if relations are normalized. We need domain knowledge to derive the determinants. We need someone with understanding of the data in the real world to tell us that column A determines column B. Do not try to do this by looking at the data. Do not try to do this intuitively, as you may read in some books, but insist on having determinants provided for you by a domain expert. Here's an example. We can say, hypothetically, that there is a value called an M number, and if you have the M number of a student, then you can get their social security number. We're saying there is a correspondence between M number and social security number. That would be a determinant. M number would be a determinant. M number determining SSN would be a functional dependency. The SSN, social security number, is functionally dependent on the M number. This also goes the other way. If we know a social security number, we can determine the M number of that same student. This information comes from the problem domain of managing student records in a student database. We don't know this unless someone tells us, someone who has an understanding of student records, an understanding of how M numbers are assigned to students. We cannot infer this. We cannot derive this from our life experience. This has to be given to us by a domain expert. Another dependency. If you give me a class, that class is a determinant for the teacher of that class. So the class that is fully defined by the semester, the year, the program, the course number, and the section can tell you who the teacher is. Semester, year, program, course number, and section completely specify one particular class being taught. And since that class has a teacher, then class is determinant of teacher, and teacher is functionally dependent on class. Let's do a more complex example. Remember, we need domain knowledge to create these examples and to solve them. So I will create a very narrow, very specific set of domain knowledge to work from. It's not quite real world. It might not make perfect sense, but it compacts into a paragraph and it's easy to understand. The XYZ company makes boats. Okay, no problem. Every boat has a unique serial number. A customer purchases one or more boats, but never more than one boat in a day. You can see we're getting a little contrived. A boat is sold by one sales rep, meaning a boat can't be sold by two or more sales reps. A sales rep may sell multiple boats in a day. So we've managed to narrow down how boats might be identified based on how they are sold. Given the previous slide, then, we can create a logical design to model a boat. Our syntax is that we underline the candidate keys. The candidate keys in this relationship are boat serial number because the boat serial number uniquely identifies a boat. The other candidate key has two columns, customer and date of sale. Remember from the previous slide, a customer can only buy one boat a day. They can't come back and buy a second boat. Even if they like the first boat, they have to wait at least one day to come back. So if we have the customer and the date of sale, we can uniquely identify the boat that they purchased on that day. A little contrived, but it works for the example. On this slide, I am giving you the logical design, which is in bold, T-boat in parentheses, the attributes, the columns separated by commas, the candidate keys underlined. And then below that, I'm giving you all the determinants. How do you know this is all the determinants? Because I'm telling you it's all the determinants. I am the domain expert. I am giving you all the determinants. Do not try to infer. Do not try to derive. Do not try to guess any of the functional dependencies or the determinants. Make sure that you trust what I give you. Go from what I give you when you solve the problem, and you'll be fine. So don't overthink these examples. That's the end of the first presentation. We've introduced the concepts of determinants and functional dependencies, a little bit about normalization. In the next presentation, we will start on 1NF, and then following that proceed to 2NF.